Hi students, we've already talked about ionic bonding, and today we're going to talk about covalent bonding, a different kind of bonding. What I'd like you to do is read and do the activity right here and stop right at this point. So pause the video and read through that first section and do that activity. Your paper should look like this at this point. So in ionic bonding, one atom has a very low electronegativity, a very low ionization energy, and the electron from that atom can get transferred to the one with a high electronegativity, a high ionization energy. Metals have low ionization energies and low electronegativities, and nonmetals have high ones. So it's always the metal electron transferring to the nonmetal. The result is that you have an attraction between your positive and negative ions, and we call that an ionic bond. When you have two atoms that both have very high electronegativity and ionization energies, meaning they both pull really hard on electrons, this kind of bonding is not what happens. We get a different kind of bond called a covalent bond. We're going to look at what happens when you put chlorine and chlorine together. So before chlorine and chlorine bond, they both have 7 valence electrons. We know that from what column they're in on the periodic table. So there are your 7 valence electrons. In order to make the bond, they're both going to pull on those electrons. They both want one more. When they both get locked in that pull and neither one is strong enough to steal the electron from the other, your result is that those 2 electrons in the middle become shared. And so we have a dot structure that looks a little different than the one we had before. There are no ions involved in this. What holds them together here is the shared pair right there. And often we actually draw this a little differently. We draw the shared pair as a line, and you might have seen that in your biology classes last year. This is a Lewis dot structure where instead of having an ionic bond, there's a covalent bond. So those 2 electrons in the middle are shared by both the chlorines. They both feel like they have 8 electrons. So I'm going to show you what that looks like. So the chlorine on the left has 1, 2, 3, 4, 5, 6, 7, 8, because the 2 that are shared feel like they belong to that chlorine. The other one, 1, 2, 3, 4, 5, 6, 7, 8, also feels like it has 8 because the 2 shared ones, both chlorines feel like they have it. In the end, all bonding happens so that atoms feel like they have an octet and they're stable. So that's still what's happening here. It's just instead of having those electrons transferred, they're shared. 2 other vocab terms, the ones that are in the middle, we call that a shared pair of electrons. And the ones that are around the outside, we call those lone pairs. The same thing happens with bromine. Both bromines have 7 valence electrons because they're in the 7th column on the periodic table. In order to make this bond, they both need one more electron, so they start pulling on the other atom's electron, but no one can win, and they end up locked in a tug of war where they share a pair of electrons. Each bromine has 3 lone pairs, so 3 sets of electrons all to itself, and then it has to share one more. They still feel like they have 8. Covalent bonds actually come in 2 types. This kind of bond is called a nonpolar covalent bond. That's because both bromines pull equally hard on the electrons. But not every bond is between 2 identical atoms. And by that I mean this is bromine and this is bromine. They're 2 identical atoms, so they pull equally hard on the electrons. But in the case if you had bromine pulling on electrons from chlorine, so the atoms are not identical, then one is going to pull harder than the other, and we call that a polar covalent bond. Please take a second and read this section down here and draw a little cartoon to show what that would look like. You can pause the video now. Okay, so these first 3 are pretty similar. I picked all atoms that have 7 valence electrons, so they only need one more to complete their octet. In order for this bond to happen, chlorine is going to pull on bromine's electron, bromine's going to pull on chlorine's electron, and then they end up locked in this covalent bond with a shared pair. But this time, it's not two identical atoms. One of them pulls harder than the other. If you look in your reference packet or on the previous page at the table of electronegativity values, you'll find that chlorine has a higher electronegativity. And so the electrons are pulled in that direction on that bond. So in the bond, instead of being evenly shared, they're pulled more towards the chlorine. The way we draw that is not just with a simple arrow, we also put a little plus sign on the end of it to indicate that this side is partially positive and this side of the bond is partially negative. We call this a polar bond. It's polar because one atom is pulling harder on the electrons in the bond than the other one. I'm going to zoom in here for a second. If we imagine that when electrons are shared, those electrons are in the middle, which they're not really because electrons are waves and particles, but when they get unevenly distributed, it's kind of like the electrons spend more time on this side, and electrons are negative, so that makes the chlorine not totally negative. It's not an ion, it's not strong enough to steal the electrons, but the electrons spend more of their time near the chlorine, so it ends up with a partial negative. Okay, pause the video for a second and do the next two, including drawing that blue arrow. So you should have indicated that fluorine pulls a little harder than bromine and that chlorine pulls a little harder than iodine. And those are both called polar covalent bonds. Now, oxygen's a little trickier. Not everything has 7 valence electrons. So oxygen has 6, and we still have to figure out how oxygen can feel like it has 8 by sharing electrons. So just like the other ones, this oxygen can pull on that one, and this oxygen can pull on that one. But the result there would be that each oxygen still only had 7, and that wouldn't be great. So what happens is these 2 electrons also get shared, and we make a double bond where 4 electrons are shared between the 2. I started by drawing 6 electrons here and 6 electrons here, so a total of 12 electrons. I've still only drawn 12 electrons over here, but both oxygens feel like they have 8. Let's zoom in for a second. So this one has 1, 2, 3, 4, 5, 6, 7, 8, and the other oxygen has 1, 2, 3, 4, 5, 6, 7, 8. Notice the ones in the bond are counted twice when you're trying to figure out how many they feel like they have. But when we count the total number of electrons, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 electrons, that's all we were allowed to draw, but we've made it so that each oxygen feels like they have 8. And that's how you draw a Lewis dot structure. Okay, let's see what happens with nitrogen. Each nitrogen has 5 valence electrons, and somehow we're only allowed to use a total of 10, 5 for each, and try to make them both feel like they have 8. I bet you can pause this and figure it out. The nitrogens end up sharing 3 pairs. So each nitrogen feels like it has 8, 3 shared pairs, that's 6. And then they have 2 to themselves, 2 electrons to themselves. So 6, 7, 8. So each of the nitrogens feels like they have 8. So the oxygen has a double bond and nitrogen has a triple bond. And both of those bonds are considered non-polar covalent. You couldn't draw an arrow pointing to which one is more electronegative because they're identical atoms. They have the same electronegativity value. Okay, take a minute and read the gray box at the top. You can pause the video. When atoms combine in ways that are a little bit more complicated, for example, making a molecule like water, then we're still doing the same thing, but there's kind of a system that'll make it a little bit easier. They're like puzzles drawing Lewis dot structures, where you can only use the number of electrons you started with, but you still have to end up having everything like touch 8 electrons. While there are lots of different systems for doing this, this is the one that we are going to use. So we're going to follow those steps. And I bet once you start getting good at them and you've done lots of practice, you're going to kind of quote unquote see the answer, because they really are puzzles. And the more you practice puzzles, the better you get at them. So let's try following those steps for something like water. So the first step says count all your valence electrons. So hydrogen is in the first column of the periodic table. It's got 1 valence electron, but we have 2 hydrogens involved, so we have to count 1 electron for each of them. Oxygen's in the 6th column, so it's got 6. I have a total of 8 valence electrons to work with here. The second step says arrange your atoms with the least electronegative atom in the center, but not hydrogen. So our only option here is to put oxygen in the middle, and then the hydrogens around the outside. It doesn't matter if you put them on either side or the top and the bottom, whatever. You just got 1 atom in the center, the other atoms around the outside. Then it says single bond all your atoms to the central atom. So we're going to just draw a single bond and attach everything to the central atom. Then it says add the rest of the electrons as lone pairs. So we had 8 electrons to start with, and so far in the bonds that we drew, we used up 4. Each bond has 2 electrons for a total of 4. Okay, so we have 4 more electrons to add. It says add those electrons as lone pairs on the outer atoms first, meaning start out here. But wait, it says not giving anything to hydrogen, because hydrogen only needs 2 electrons. That's because it's in the first principal energy level. We call it an octet rule violator. Bottom line, hydrogen only needs 2 electrons. So those 2 hydrogens actually are already perfectly happy. Draw a little happy face to say they're good to go. We don't have to do anything to them. But the 4 electrons we have left, we're going to put as lone pairs on the oxygen. It says fix any octets with multiple bonds. So let's just double check that oxygen has an octet. If we are counting oxygen's electrons, it has 4 electrons in lone pairs, and then each of the bonds makes it feel like it's touching 4 more. So oxygen's actually totally happy with this situation, right? 1, 2, 3, 4, 5, 6, 7, 8. So oxygen's happy too. So we're good to go here. Okay, let's check out another one, CF4. So the carbon has 4 valence electrons, and then each of the fluorines have 7. So I'm going to add those all up, and I get a total of 32 electrons to work with. I'm going to arrange my atoms with the least electronegative atom in the center. So carbon is much less electronegative than fluorine. It's also usually the atom that you only have 1 of. We'll put carbon in the center, and I'm just going to draw the fluorines around the outside. Now we're going to single bond everything to the central atom, so just a single bond. Each of those bonds is 2 electrons, so far we've used 8 electrons. 2, 4, 6, 8 electrons. Remember, we started with 32 electrons. That's how many valence electrons we had to work with, and we've used up 8, so that gives us 24 electrons left to use. And step number 4 says to add the rest of those electrons as lone pairs on the outer atoms first. So I'm going to add those 24 electrons. I'm going to add them evenly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So I've added 24 electrons, and we had 8 in the bonds. So now all 32 electrons are drawn on here. And now we're going to check to make sure that things have an octet, right? So each of the fluorines are identical the way they're drawn, and they have 3 lone pairs, that's 6. And they're each touching a bond, 7, 8. So all the fluorines feel like they have 8, so they're good to go, right? So we can say the fluorines are totally happy about this. And then carbon is touching 4 bonds. Each bond is 2 electrons. So carbon also feels like it has 8. So that's good to go too. So we don't actually have to fix any octets, which would be step 5. But we should practice one where we do have to fix an octet. So let's try that with carbon dioxide. Carbon brings 4 electrons and oxygen brings 6 electrons. And we're not talking total electrons, just the valence electrons. So how many valence electrons are involved? So we've got 16 electrons to work with here. And so we're going to follow the same steps. Okay, so we're going to place carbon in the center because it's the least electronegative, the oxygens around the outside, and we'll single bond them both to the carbon. Now we've used up 4 electrons. We have 12 left, so I'm going to add those 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the directions say to add those electrons as pairs and start with the outer atoms. So that's what I did. I started with oxygen. I haven't put any on carbon, and actually I don't have any left. Right now, this picture as it's drawn right now has 16 electrons drawn. But there's a problem. Carbon doesn't feel like it has 8. Both of the oxygens are totally happy. They are touching 8 electrons, but the carbon is not. So this is where we have to do step 5, fix any octets with multiple bonds if necessary. So what we're going to do is we're going to take some of those electrons that oxygen has all to itself, and we're going to make it share. So each of the oxygens is going to have to share a set of their electrons, and you're going to end up with 2 double bonds. We can't add any more electrons. We're only allowed to use 16, so we're just moving some of the electrons that we drew. So instead of being like that, it's going to have a double bond there. And you can double check, make sure we still have the right number of electrons. We're only allowed to have 16. So you can take a second and count them, but there are only 16 here. And here are the ones.
Is there something else I can help with?
Here are the ones right here, right, that got swung in, and we still have 16 electrons, but now everything has an octet. Each of the oxygens is touching 8 electrons, and then the carbon also is touching 8. It's got a double bond on each side. So that's 4 bonds total that it's touching. Each bond has 2 electrons, so that's 8 also. Just a quick reminder, all these bonds are polar covalent bonds, right? Because they're all between 2 different atoms. So I could go back in on any one of these and draw my polarity lines, figuring out which one's pulling harder on the electrons. Oxygen pulls harder in this case than carbon does. So the oxygens have a little bit more hang time with the electrons over here. Fluorine pulls a little bit harder than carbon. So my polarity lines would point towards the fluorine. And the little like positive tail of my arrow would be over by carbon. And then in the water molecule, the oxygen pulls a little harder on the electrons. And we'll learn later on that this is what makes water a polar molecule. But right now we're just going to focus on the bonds. The bonds are polar. So there we go.